Swayam Prabha. Digital India. Educated India.
Next, we will go ahead and see what are the equilibrium equations that the stress field has to satisfy. Till now we have assumed that the stress is acting uniformly, there is no difference between the positive normal and negative normal faces of the stress cube. When the stress varies spatially, there will be a difference between the stress acting on the positive normal and the negative normal, and we want to see what happens then. Okay. Now we are moving on to look at two dimensional equilibrium equations. Okay. Now there are two kinds of forces that can act on a body. One is what is called as a contact force, that occurs due to contact, just like if I apply a force here on the table, it is my hand is in contact with the table and hence I am applying a force, that force is called as a contact force, and second force is called as body force. This does not occur due to contact, this occurs through action at a distance kind of a concept, wherein the earth attracting a body to fall on its surface is an example of a body force. The gravitational force is an example of a body force, so are electromagnetic forces. These are action at a distance forces. Okay. Example of them are gravitational force, electromagnetic force. Okay. Now let us take a two dimensional plane stress element. Okay. Let us take a two dimensional plane stress element. Let us assume the coordinate system is oriented at the center of this element, let it be Ex, Ey. Now you know that the components of the stress cube are, there will be a sigma xx acting here. If the stress were to be uniform, there will be a sigma xx here too, okay, but the cube has a dimension of delta x which is infinitesimal but significant. Okay. So hence the stress acting here would be sigma xx plus d sigma xx by dx into delta x. Let us assume that to be the stress there. Okay. And then similarly let sigma yy act here, then the stress acting here would be sigma yy plus dou sigma yy by dou y, because there is a variation along the y direction here between the bottom face and the top face into delta y. Okay. Similarly I have the shear stresses, this will be sigma xy, this will be sigma xy, and it will be sigma xy plus dou sigma xy by dou x to delta x, because here the variations along the x direction. Similarly I will have this is sigma yx, this will be sigma yx plus dou sigma yx by dou y into delta y, okay, and this stress would be sigma yx. Okay. Apart from these stresses that are acting over the respective areas, there is a body force. Let us assume that this body force is, let us assume that there acts a body force B along at the CG of the element, wherein Bx would be the component of the body force along x direction, By would be the component of the force along the y direction. Okay. Now this body force is usually defined per unit mass, usually defined per unit mass for understandable reasons, because you are more interested in the gravitational force which depends upon the mass of the body. Okay. Hence this cube is travelling at a velocity of v with an acceleration a, okay, with an acceleration a in the plane of the diagram, okay, in the plane of in the same plane. Okay. So now if I, for this cube to be in equilibrium, I require the sum of all the forces to be 0. Okay. Let us say I am interested first in sum of forces along the x direction. Okay. Then what I will get is, I will get the forces that are acting in the x direction are sigma xx and sigma yx. Okay. So I will get sigma xx plus dou sigma xx by dou x into delta x minus sigma xx into the area over which the stress acts. Okay. The area over which the stress acts is this area, that will be delta y times into the plane which will be delta z. Let us assume that the cube is having a dimension delta z in the z direction. Okay. So this will be delta y into delta z, because I am assuming a cube like this, wherein this dimension is delta x, this dimension is delta y and this dimension is delta z, and my coordinate system is Ex, Ey and Ez outside the plane. Okay. So this will be one of the component of the forces. The other component of the force would be this sigma yx component of the force, which is acting on this plane, the top plane, hence this area would be delta x times delta z, hence this component will be delta x times delta z. So that will give me plus, that will give me plus sigma yx plus dou sigma yx by dou y into delta y minus sigma yx into delta x delta z, plus there is a body force rho whose component along x direction would be denoted by rho bx into its mass. Okay. So I will write the mass as rho times delta x delta y delta z, where this is the volume, this is the density, delta y delta z is the volume of the cube, and hence this product will be the mass of the cube. Okay. This should be equal to the inertial force that is applied on the body. Okay. So the inertial force would be the mass times the component of acceleration along the x direction, which I denoted by Ax, times the mass, which by the same argument will be rho times delta x delta y delta z. Okay. So simplifying this, you will get that dou sigma xx by dou x plus dou sigma yx by dou y plus rho bx must be equal to rho Ax, where the volume of the cube I have cancelled throughout. Okay. Following a similar approach for the same cube, I am going to write the equilibrium equations along the y direction to be equal to Fy inertial force. Okay. Here the force that are going to contribute are sigma yy and sigma xy here. Okay. So I will get sigma yy plus dou sigma yy by dou y into delta y minus sigma yy into the area over which it acts, which will be this delta x delta z, because this is the area on which sigma yy acts. Okay. So that will be delta x delta z, okay, plus the shear stress contribution, which will be sigma xy plus dou sigma xy by dou x into delta x minus sigma xy, which acts on this phase, that will be delta y times delta z will be the area on which it acts. So, that will be delta y delta z plus the component of the body force along the y direction, which will be body force into delta y delta x delta z, which will be, since body force is different per unit mass, this is the mass of the body, which gives me the net body force acting on this cube should be equal to the y component of the acceleration into its mass, which is rho times again delta x delta y delta z, right. So, simplifying this further, we will get the equation dou sigma xy by dou x plus dou sigma yy by dou y plus rho times by will be equal to rho times ay. So, if this is the first equation, this is the second equilibrium equation. In a plane problem, you have two force equilibrium equations and one moment equilibrium equation. So, let us see what the moment equilibrium tells us. Okay. Next, we are going to say what is the moment equilibrium, mz moment equilibrium taking anticlockwise moment as positive. Okay. Now, I can take the moment equilibrium about any point, but I am going to take about the Cg of the element. Okay, I am going to take the moment equilibrium about the Cg of the element. The reason being, we take it about the Cg of the element about this point, the sigma xx, sigma yy, the body force and the inertial forces will won't contribute to the moment balance. Okay. So, only the shear stresses are going to contribute to the moment balance. Okay. So, what is that you get is you will have this sigma xy, this sigma xy shear stress acts in the phase delta y delta z and acts at a distance of delta x by 2 delta x by 2, and it produces a moment which is a anticlockwise moment. So, that moment is positive. Okay. So, we get sigma xy plus dou sigma xy by dou x into delta x into the lever arm, which will be delta x by 2 plus sigma xy to lever arm, which is delta x by 2 into the area over which this shear stress acts, which will be delta y delta z. Okay. This anticlockwise moment has to be balanced by the clockwise moment produced by sigma yx, produced by this stress, this shear stress in here. This produces a clockwise moment. So, that moment would be minus sigma yx plus dou sigma yx by dou y delta y into delta y by 2 plus sigma yx into delta y by 2 into the area in which it acts, which is delta x delta z, has to be equal to 0. Okay. This equation was simplified to sigma xy minus sigma yx plus dou sigma xy by dou x into delta x by 2 minus dou sigma yx by dou y delta y by 2 to be equal to 0. Okay. In the limit when delta x and delta y tend to 0, you will get the restriction that sigma xy must be equal to sigma yx. Okay. So, this is what we are referring to as the stress tensor being symmetric due to the moment balance requirement. Okay. So, to recap, in plane state of stress, for plane stress we derived the equilibrium equations to get dou sigma xx by dou x plus dou sigma yx by dou y plus rho bx equal to rho ax, and then dou sigma xy by dou x plus dou sigma yy by dou y plus rho by must be equal to rho ay, then we got sigma xy equal to sigma yx. Okay. In 3 dimensions we will show that the same equilibrium equations for 3 dimensional stress state will be written as divergence of sigma plus rho b equal to rho a, and the moment balance will tell us sigma equal to sigma transpose, where this divergence of sigma is nothing but dou sigma xx by dou x plus dou sigma yx by dou y plus dou sigma zx by dou z, dou sigma xy by dou x plus dou sigma yy by dou y plus dou sigma yz, dou sigma zy by dou z, sigma xz by dou x plus dou sigma yz by dou y plus dou sigma zz by dou z plus rho times bx by bz equal to rho times ax ay az. In the next class we will see a detailed derivation of this equation along with the condition that the moment equilibrium will tell us sigma xy equal to sigma yx, sigma xz equal to sigma zx, and sigma yz is equal to sigma zy. Okay. We will see a detailed derivation of this, but before we conclude I want to just point out that the derivation here that we saw is not mathematically rigorous, because it looked like there was no restriction on the stress field for us to get the equilibrium equations, but we had tacitly assumed when you wrote the stress field as given here as a first order Taylor series expansion, when you wrote the stress field using a first order Taylor series expansion as this, that the higher order derivatives are have a magnitude which is lesser than the first derivative. This is not always true. Okay. Let me give you an example. Let us look at a function form f of x f of r to be r power 3 by 2 in the domain 0 less than r less than 1. Okay. Now df by dr is 3 by 2 times r power half, and d square f by dr square is 3 by 4 r power half. Clearly the second order derivative and higher order derivatives have values more than the first order derivative. It does not mean that if the stress field were to vary like this, it is the inapplicable stress field to write the equilibrium equations. Okay. And hence in the next class we will see a rigorous way of deriving these equilibrium equations without any assumption, and show that it holds only when the stress field is continuously differentiable in the interior of the body, that you can get the equilibrium equations as divergence of sigma plus rho b equal to rho a. Okay. Thank you.